Okay, so before we get into it, just want to kind of point out a few things. I can't remember how much I went over on Wednesday, but the final exam practice materials are up on Canvas. I updated that final formula sheet, so it has a couple things that got chopped off in the first time I uploaded it. Look at the in-class data. I'll be working off this GPA data today. We did a little bit on it last class. I'll add some more to it. I'll then kind of re-upload it here with like GPA data in-class work after today, okay? So after today, we should have everything you would need to then, if you want to, if you have, if you missed one of the first 4 assignments or wasn't happy with one of your grades, you can use those kind of 5th assignments to replace your lowest, or, if you're happy with your grade, you don't have to do them, but they're a good review for the exam as well. And after today, you should be able to get through, all the questions on there, okay? So I believe where we left off was kind of, I think I ended class with introducing this idea that, we can run these simple linear regressions where we have one X variable, right? One right-hand side variable, but we can also include additional variables. So, if you think about really what we're trying to do, and I'll set this up with the dot cam here. Take a second. And I'll set this up with the first thing in the slide. So let's say, I don't know, we're trying to predict crime rates, right, as a function of how much is being spent on the police force, right? So if you tell me any value, like if you told me, like once I obtain these numbers, right, I run this regression using some sample data, I don't know, maybe I get something like, I don't know, the intercept is 20, and then here it's 5 times police, right? So if you tell me, once I get these values, these coefficient values from Excel, you can tell me any amount of police force expenditures, and I can come up with a predicted crime rate for that county or state, right, depending on the example. Well, if I'm trying to come up with predictions about crime, yeah, the amount of money spent on the police force probably matters, but there's a lot of other things that probably matter as well. So I probably want to include, a bunch of additional things. So maybe here, I now think about, I can also include something like, what's the unemployment rate in the area, right? What's the economic conditions? Because we know that those drive different, crime rates as well. So we want to include more things there on the right-hand side so that we can come up with better predictions of that Y variable. Now we can include as many variables as we want here, right? X, all the way up to N, right? And then, we can think about, all right, if I was to have ran, let's say, I'll introduce the idea of causation and correlation at this point. So let's say I would have just run the simple linear regression with just police expenditures, right? So I run this regression, and I end up finding that beta 1 is positive. Well, why would it be that if I spend more on my police force, that crime actually goes up? Seems kind of counterintuitive. Well, that's because what beta 1 ends up doing, and we'll go a little bit more, go a little bit more in detail in a little bit, but what beta 1 is capturing, right, when I don't include that unemployment variable, is it includes all the other effects of variables that I left out of the equation if they're correlated with police force expenditures and crime. So, when there's higher unemployment, it's likely that there's going to be more crime and that requires police force expenditures to be higher. And so if I don't control for that, my coefficient on beta 1 was going to be what we call bias. We'll dive into this a little bit more in a second, but the idea is if I can include it, well, now that beta 1 no longer includes that bias. It no longer picks up the effects of unemployment rates. It's just picking up the effects of police force expenditures. Now, maybe it's picking up some other important things that we're leaving out, but at least now the bias that existed because of not including the unemployment rate, by including it in our regression, we get rid of that. So we've got this equation, multiple right-hand side variables now. So just like before, well, actually, let's go back to last class. Last class I said, we've got what we're really trying to do is we're making these predictions. For any one observation, our predictions are going to be off. So we've got error terms, right? We're making errors for every single observation. Our predicted Y is different from the actual Y. So what we want to try to do is get this line of best fit that minimizes the sum of those errors squared. So if we rewrite that, we can see we have these two things to choose. So we have to minimize this equation, choosing A and B, take two derivatives and take a derivative in respect to both those things, set them equal to 0, two equations, two unknowns. We can then find the solution that would give us that slope coefficient B. Well, we can do a very similar thing with multiple linear regression. It's just now instead of taking the derivative in respect to two things, I've got n, a number of things. So now I've got n equations and unknowns. I can still solve. It's going to be a lot messier math, but I can still do it. All right. If you're a little bit more interested in this, I'm not going to waste time in class, but here's kind of a nice little mathematical proof and walk through about no matter how many variables you have, what the actual formulas would be for those slope coefficients. But all you need to know all we need to know, I guess, is that we can do this in Excel. And Excel will do all that computation behind the scenes, right? I broke it down last class into like, you couldn't do it step by step, but why, right? Because that data analysis tool will do it all behind the scenes for you. And once we see that Excel output, our interpretation of the coefficients largely remains unchanged. So the interpretation is still going to be for any coefficient. That coefficient is the expected change or the predicted change in Y from a 1 unit change or 1 unit increase in X. But now we add on holding all else constant. So everything else in the regression that I have, hold all that constant, and then the interpretation of the coefficient is the same. For the intercept, the interpretation is going to be, before it was, this is the predicted Y value if the X variable is equal to 0. Well, now it's just the predicted Y value if all the X variables are equal to 0, right? Because if all the X values are equal to 0, if 0 times anything is 0, we're just left with that intercept. So it's pretty much the same interpretation. We just have to say all X variables equal to 0 for the intercept, and for any slope coefficient, we have to add on this phrase, holding all else constant, okay? So we're going to take a step back here. I'm going to kind of go out of order a little bit in the slides. So we'll go here to the raw data. So this is what we did last class. So I'm going to rename this regression from 421. Here's our data. So what I'm going to start out this example with, and like I said, I'm moving all kind of around the slides a little bit, but I think it's going to be better to go through things this way. What I'm going to start out doing is say, okay, I'm going to try to predict GPA, and I think it's going to be a function of kind of whether or not you're a student athlete. And I might be interested in this question because I don't really know the sign of that slope coefficient. Being a student athlete, if I think about this as just a 1, 0 variable, so the 1 unit change, similar to when we looked at the mother smoking variable last class, is if I go from being not a student athlete to being a student athlete, right, going from 0 to 1, here's the predicted change in GPA. Now, it could be positive. Maybe being a student athlete teaches you time management. You have to be more on top of your grades, but it also just requires a lot of time. So maybe it's a negative, right? So we go to, I guess I can leave this up here. We go to our data tab, data analysis, scroll down to regression. Our Y variable is college GPA. So Control Shift or Command Shift on a Mac, select that, enter. My X variable, I'm going to actually look at whether or not they're a student athlete, okay? So I'm going to hit OK, or I selected my labels, hit OK. We're going to call this, rename it as naive. This is a naive, because this is a naive regression. So here, if we look down here, going from 1 unit change in this athlete variable, going from 0 to 1, so being a student athlete relative to not, predicts that the GPA would be about 0.28 lower. And this is a reminder, right? We can reject the null if the p-value is less than alpha. Well, here the p-value is, move that decimal point 9 places to the left, so basically 0. So I can reject the null at any level, but we have to remind ourselves, well, what's the null? For every regression, we always assume that those slope coefficients are equal to 0. So if I fail to reject that, then the relationship between athlete and GPA, I can't reject that it's anything other than 0, anything different from 0, or that there is no relationship. Right? But here, I found a p-value that's less than alpha, so I can reject this. So if I'm rejecting the null, that means I'm saying I'm rejecting that there's no relationship. I found evidence that there is a significant relationship, that there is some, the slope coefficient is something other than 0. Okay. So, here we're like, well, don't tell your kids to play athletics in college, right? It has a negative impact on GPAs. But I called this a naive regression because there's likely a lot of other things that would be helpful in predicting GPA, right? And one of the things, especially if we're looking at sample data that comes from D1 or Division I universities, is that maybe some of the top athletic programs are maybe a little bit more lax on their academic standards. If we were thinking about kind of big college basketball and football programs, or maybe, a lot of the, maybe some of the teams are actually, hold their student athletes really accountable. So maybe that, they tend to have higher on average intellectual ability. So we think that maybe, right, the academic standards or quality or intellectual ability might vary from student athletes relative to the general population. So let me go back to this. And anytime you want to run, I think I might have mentioned this in the class, anytime you want to use variables that or include multiple variables on the right-hand side, they need to be right next to each other. So I want to now include athlete, but I also want to include what their SAT score is. Okay. So I'm going to insert a cell here. I'm going to move this one over. And actually, I don't want to use this for a while, so I'm going to move the SAT squared all the way to the end of the data set. And I'm going to minimize this so I can scroll over, and we'll delete this. Okay. So I'm just moving my columns around so that now I can go to that data analysis tab. My Y variable is still GPA, but now my X variable, I want to include both SAT and athlete. So once again, Command Shift on a Mac or Control Shift, hit the down arrow, selects both those variables for me, hit OK, zoom in so we can see it, and now we get that the effect of being a student athlete relative not to being a student athlete, all right, the 1 unit increase there, is that the predicted GPA falls by 0.05, holding the SAT score of this individual constant. So this is a lot more powerful because now the thought experiment is we have two individuals hold constant the SAT score. So they have the same score on the SAT, but one of them is an athlete, one of them is not. We would predict the athlete's GPA would be about 0.05 lower. That's a lot more powerful than just say being a student athlete, right? Because there you're not controlling for any differences that might exist in the kind of intellectual or kind of starting point, intellectual ability or the starting point of these athletes relative to the non-athletes. And if we look at the p-value here, well now we can't actually say that a student athlete's GPA is any different from a non-student athlete because the p-value is 0.25. That's not going to be less than any alpha we typically look at, right? It's not less than 0.01, not less than 0.05, not less than 0.1. So we fail to reject the null. Well, if we fail to reject this, we're not rejecting this. What we're saying is, yeah, the true relationship between being a student athlete and GPAs could be 0, right? So just by including one additional control variable, we eliminated that bias that existed and we find a completely different effect, right? We went from finding a pretty significant negative effect to basically we can't say that there's any relationship between being an athlete and GPAs. So we'll rename this naive 2 because, yeah, it's great. We're now controlling for SAT scores. We're thinking along the right lines. But we got a lot of other data here, right? We have a lot of other variables that think that, their high school ranking or the number of credit hours, all these things probably have an impact on GPAs as well. So what I'm going to do next is, well, I've got the data, right? I'm still using that GPA as my Y variable. I'm just going to throw the kitchen sink at it. I'm going to include, what their high school rank was, their score in this verbal math test, their gender, race identifiers, total credit hours I took, their high school size, right? So Control Shift or Command Shift on a Mac. Just select all those variables. Now I can control for a lot more things. So now when I go to look at my regression results, now I look at that student athlete variable and I say, well, look, now being an athlete relative to not being an athlete predicts that the GPA is actually 0.17 higher, right? And the p-value is 0, so I can reject that null. I can reject that there's no relationship, or I found really strong evidence that there is a relationship between being a student athlete and GPAs. But by controlling for a lot of other factors that probably matter, I now end up getting like a more accurate depiction of what that relationship is. When I was running these naive regressions, this coefficient was picking up the effects of all the important variables that I was leaving out. Right? So now the thought experiment becomes, right? Here's the predicted increase in GPAs from being a student athlete, right? That 1 unit change, holding everything else constant. So 2 people with the same SAT score, same rank in their high school, scored the same on this verbal math test, both female or both male, both white or both black, total same number of total credit hours, they went to the same high school of the same size, but one of them's a student athlete, we would predict their GPA would be 0.17 points higher. That's a lot more powerful of a statement, right? So holding constant all these factors, we get a much better estimate of what the relationship is between each one of these variables and that Y variable GPA. We can also make better predictions, which I'll go through here in a little bit, but for now, we'll just kind of leave it there. Okay. So with this idea in mind, we'll kind of go back to the slides, and I skipped this R-square slide. We'll come back to this. So I kind of already discussed this idea of causation and correlation with this original example. But let's think about one we used from last class. So let's say I'm trying to predict birth weights, and the only X variable I have is whether or not the mother smoked, right? I can guarantee you anytime you run this regression, just like when I showed you the results last class, that slope coefficient is going to be negative, right? Smoking while pregnant has a negative impact on birth weights. However, you know, I think last class was like 250 grams or something like that. It decreased the birth weight by. But the problem is we've left out a lot of important variables, right? Birth weight of a child is, you know, a lot of other influences than just smoking while pregnant. So one that we could think of that would be, you know, a good idea to include is maybe the income level of the mother, right? So higher income levels, right, have more access to healthcare, more access to higher quality foods, you know, a lot of, you know, more access to, I don't know, prenatal care. So higher income levels are going to impact birth weights, but they're also going to decrease the likelihood a mother smokes while pregnant. Like if we look at the correlation between smoking while pregnant and income levels, lower income levels have increased likelihoods of smoking while pregnant. Lower education levels have higher likelihoods of or higher likelihoods of smoking while pregnant. So if we don't include education or income controls, this smoking variable, mother smoking while pregnant, is going to pick up the impacts of those as well. So yeah, smoking while pregnant is probably going to always have a negative coefficient. But if I don't include these things that I also know have negative impacts on birth weights, like lower education levels, lower income levels, it's going to pick up those effects as well. So it's going to kind of exaggerate the impact. So I'd want to control for those, you know, to get a more accurate idea about what this relationship between birth weights and smoking while pregnant is. Another good example is, you know, here I've got a little infographic of like, if I have this data set and I ran a regression where I've got autism rates and organic food sales, this is going to be a very strong, significant positive effect. But, you know, if my Y variable is autism rates and my X variable is organic food sales, do we really think that organic food sales are causing autism rates to be higher? I mean, it doesn't make, I don't know. I don't know what the connection there would be. It doesn't make a lot of sense. What's probably a lot more likely is there's an outside factor, a third variable Z maybe, that's causing both of these things to go up, right? So these two things will always be correlated, right? It's kind of like, going back to the first week of class, I used the example of, you know, drowning deaths and ice cream sales. Those two things will always be positively correlated. But it's because there's a third factor, which is temperature, that's causing both of them to go up. So here, autism and organic food sales are probably going to be positively correlated, but that's because there's this outside factor of an increased focus on our health or an increased focus on you know, health care that's maybe causing both of these to increase. Okay? So we want to make sure that if we do run a regression, we want to make sure that we remember this is evidence of a correlation, not necessarily causation or not causal. Okay? So it could be that X and Y, right, are both increasing because Z is causing both of them to change. and we didn't include Z in the regression. Now, if we include Z in the regression, well, now we could get an accurate idea of what the correlation is between these variables X and Y. So I always kind of think the little cartoon of this always made sense, or I always thought this was funny. So I used to think correlation implied causation. Then I took a statistics class, so now I don't. Well, it sounds like the class helped. Well, maybe, right? Because maybe it was some outside factor that caused them to understand the difference, but also caused them to take the class, right? So we've got to make sure that we try to include, right? This kind of highlights, we need to try to include as many variables as we have, kind of data on or that we think will be relevant to predicting this Y variable. So I've got kind of a more formal slide in here that kind of, walks through line by line, but really the synopsis of this was that if I'm going to run a naive regression where I only include one variable on that right-hand side, when I get my results back from Excel, that estimate for what that relationship is will include the true relationship between this X variable and the Y variable. But if I leave out this other important variable X2, it's also going to pick up this biased component, right? It's going to pick up part of the effects that this variable I left out was going to be having on GPAs. Now, once I include that second variable, this bias term goes away, right? So if we can include, a lot of variables that are good at predicting our Y variable, we can kind of make sure that we're eliminating a lot of the bias that exists in those coefficient estimates that we have, okay? Or those slope coefficients. So I kind of already walked through this example with the athlete and SAT. I've got kind of a reminder how you get that data analysis option in there. I'm going to go back before we kind of tackle this. Are there any questions up to this point? Anything that we've kind of talked about that you're just maybe even curious on, or, oops, I did not mean to minimize that so quickly. Okay, all right, so we have one more statistic that we're going to pay attention to, and this is called R squared. So R squared ranges from 0 to 1. A lot of the times you might see it displayed as ranging from 0 to 100 because it represents the proportion of the variation in the original Y variable that we can explain using the variables we included on the right-hand side of our regression equation. Right? So say it's a little bit different, and we'll kind of walk through it. So the way you calculate this R squared, this should look kind of familiar. We're looking at the actual Y. So if we looked at that GPA variable in the data set, the actual Y values, and we look at the deviation from the mean, and then we square it and then add them all up. Well, this is the numerator of our variance equation. So this is really capturing what the variation in that Y variable is. So this is kind of like how much variation is there, that's our denominator. Now, if we look at our predicted Ys and see their deviation from the mean squared, well, this is going to tell us how much variation exists in our predictions. Well, if our predictions were perfect, well, then the predicted Y would just be the actual Y. The variation we would see would be the same variation we see in the Y variable. The problem is our predictions are quite often not right? We've got there is an error term there. So the numerator here, this difference between the predicted Y and the average Y, is going to pick up the amount of variation based off in our predictions that were based off of the X variables we included, divide that by the total amount of variation that exists in the actual Y, and we can think about this is the proportion of the variation in that Y variable we're able to explain with all the X variables that we included in our regression to make our predictions. Okay. So, excuse me, let's take a look, and maybe this makes a little more sense when we go back to what we've already done. So I'm going to move this over and rename this. This is where we threw everything. So we threw the kitchen sink at it. So let's look at this naive regression where we only included student athlete, right, and try to predict GPA. There's a lot of different R squareds in this output, or what look like R squared, but here is the actual R squared, right? Multiple R and adjusted R. Those are things for topics for kind of outside this class, kind of probably that would be the next kind of set of things we might cover. But for us, we're just going to focus on that R squared. So I said it's going to be between 0 and 1. Kind of 1 would represent we can explain 100% of the variation in GPAs. Well, here, using a student athlete, I'm only able to explain what, 0.008 of the variation, or 0.8%, right? If I'm trying to say this is a percent, I move the decimal 2 places. So I'm hardly explaining any of the variation that exists in GPA using just student athletes. So my predictions are basically pretty far off, right? I'm not capturing a lot of what I would need to in order to make accurate predictions, right? So I'm not capturing a lot of that variation in GPA. If I then simply go and I include just one more X variable, which was the SAT score, notice now the R squared, well, now I'm up to about 0.17, or I'm explaining 17% of the variation in GPA. So I'm doing a lot better, right? SAT was really helpful. It's really good at being able to help predict GPAs. Then when I throw everything at it, what do you think probably happens to the R squared? Well, if I'm just including more variables on the right-hand side, if I have more information on the individual, I'm probably able to make a better prediction about what their GPA is. So, sure enough, when I include all of those regressions, my R squared is up to almost 30%, right? I'm explaining 30% of the variation that exists in that GPA variable, okay? Any questions on that before we keep moving here? So really you can think about it as a higher R squared means that we're making more accurate predictions, right? Or we're explaining a higher percent of the variation in that Y variable. So the next thing we're going to do is I am going to, so let's think about what we were doing here. Let me make sure we can see all this. There we go. So our regression equation here was we had our GPA plus the intercept plus the slope coefficient on SAT score times SAT score plus the slope coefficient on athlete times being an athlete plus the coefficient on high school rank times high school rank. And we would do that for the rest of our variables, right? So once I run this regression, I get these coefficient estimates. I could plug those into this equation. Then if I told you there's this hypothetical person and they got, a 1200 on the SAT, not an athlete, 12th ranked in their high school, right? So on and so forth. I would then have coefficients that I could plug into this regression equation. And then this hypothetical person, I could plug in these values for the X variables and come up with their predicted GPA. So I want to try to predict this hypothetical person's GPA. So I'm going to go up here and I'll show you kind of an easy way to do this. So here I'll say, here's the hypothetical person. So what are they gonna have, right? Well, maybe they got a 1200 SAT score. They're 13th ranked in their, oh, that's a student athlete variable, sorry. They're not a student athlete, ranked 13th in their high school. This verbal math score, if I remember right, it kind of ranges from like 0 to 2 or something goofy. Like, so we'll just do 0.9, right? Actually, I think it's probably measuring how many standard deviations away from the mean they are, but we'll just keep going. We'll say that they're female, they're not white, they're black, it's 55 credit hours. And their high school size is kind of, it's not in the thousands. They like divided it by 1,000. So I think something like 4.6 would be 4,600 people in their high school, or maybe it's 460. I can't remember exactly, but at least that makes sense for looking at that high school size variable. The things are kind of ranging here, right? That's a value that makes sense for us. So I've got this hypothetical person that have all their X values. Now it's just a matter of taking each coefficient, multiply it by that hypothetical person's value for that variable, and then adding them all up. Also, don't forget to add in the intercept here, right? So I'm going to go over here and call this, right? I'm just taking the coefficient, multiplying it by the X variable. Well, for the intercept, I just got to put the intercept in there, right? For every other variable, I'm going to take that coefficient on that variable and multiply it by whatever the value of that person had for that X variable. I can then copy this down, do that for every single variable. And then the last step is just add everything up, right? So I'll just add these all up. And I get the predicted GPA of this hypothetical person. Okay. So, you could do this by hand, like in a calculator, but if you've got these coefficient estimates here and you just kind of enter in this hypothetical person, it makes it pretty easy to do this in Excel. Okay. Any questions on that before we keep moving here? Pretty good on time. What did I want to mention here? Oh, and if we wanted to, what we really could do is go through, look at the actual Y, and for every single individual, we've got their values for the X variable. So take those coefficients and come up with a predicted Y for every single person, right? Every single observation. We could then look at the difference between the actual Y and the predicted Y. We could use those predicted Ys, find their deviation from the mean, right? And if we come up with a prediction for every observation, that basically helps us calculate that R squared, right? So Excel kind of does that behind the scenes for you. But really, for any one person in your data set, you could come up with a predicted Y variable or predicted GPA and compare it to their actual GPA. All right, so the next thing I might ask you to do, or I do ask you to do on the exam or on that Excel assignment, that 5th Excel assignment, is make a rejection decision, right? Or determine whether or not, which of these variables can I say there's a significant relationship between those variables. And actually, I'm going to delete these columns because we don't need them right now, and I want you to be able to see everything. So which of these variables have a significant relationship with GPA, right? And I say they have a significant relationship if I can reject the null. Right? So let's say we want to know at an alpha of 0.05, so the 5% significance level. Right? Well, I could go through by hand and check all these, right? So for the SAT score variable, e to the negative 107, this p-value is pretty much 0. So 0 is less than our alpha of 0.05, so I'm rejecting the null hypothesis, which means I'm rejecting that there's no relationship, or I'm saying there is a significant relationship between SAT and GPA. And then go to the next variable, athlete. It has a p-value of 0, so I would reject the null there. There's a significant relationship. Then I look at one like the verbal math score, 0.1. That's not less than my alpha of 0.05, so I fail to reject. Well, if I fail to reject, I'm really saying the relationship, I can't say that it's not 0. There could be no relationship there. So I would say that's not there's not a significant relationship between that verbal math test and college GPAs. So I could go and do this by hand, but these e's to the negative, I could make up, 3.8, that's a high p-value. Well, I forget that can't have a p-value over 1, but doing this by hand, I could make some errors. So if you wanted to, we could make it a little bit easier. We could use that if statement, right? I've been trying to use this a little bit more because I think it is helpful, right? So take that p-value. Is it less than the alpha I've chosen? Comma, if it is, put in the word reject. Comma, if it's not, put in the word fail. And I'll know that means fail to reject. Now, when I copy this down for every variable, I want to use, update the p-value, but the alpha value should keep staying the same, so I'll freeze that cell. So once I have this rejection decision in here, now I can kind of easily, quickly see, every time I reject, I'm saying, okay, I'm rejecting that there is no relationship, so I'm saying there is a significant relationship. So the only time when there's not a significant relationship is if I fail to reject. So the only two variables that don't have a significant relationship with college GPAs are whether the individual is white and this verbal math score, right? So it looks like race doesn't matter as much for GPA, but also that this verbal math score isn't a good predictor of GPAs either. Now, if I'm in an admissions department, I probably go to this school and say, well, look, I don't know why you're using this verbal math test to try to get a good idea about how well students are going to do, because it's not statistically correlated at all with college GPAs. It's not a good predictor at all. So these are likely two variables that we don't think have as much influence, or at least we want to be careful with the causal interpretation, where they just don't have a high correlation with GPAs. They're not as helpful at making useful, or they're not as useful at making good predictions of GPA. Okay. But that's a nice, quick way we can make rejection decisions. Let's see, would these change? So we don't have any kind of intermediate p-values here, but I could change the alpha up here to 0.1 or 0.01. but I don't think any of the rejection decisions change here because the p-values are either really small or they're too large. Okay. Any other questions here? Okay. What do I want to do to end this out? So I think that we've kind of covered everything. Like I said, I know I jumped around a little bit today, but we got the correlation versus causation, R squared, looking at multiple regressions. So I want to go back and just use this example and then show you a couple things. Oh, nope, sorry. Naive 2 is the one I want. So I just kind of show you how to make predictions, and maybe it kind of seemed tough, but if we do it with a smaller data set, maybe it'll make a little bit more sense. So let's say, you know, I'm trying to predict GPAs, and I've got the intercept plus the coefficient times SAT plus the coefficient on athlete times whether or not they're an athlete. It'd be really simple to say, okay, well, if I've got someone that has an 1100 and they are a student athlete, or sorry, what's their predicted GPA? Well, it would just be the intercept plus that coefficient on SAT times their SAT score plus the coefficient on student athlete times, well, if they're a student athlete, that's a 1, right? So we'll hit enter. So I can come up with predictions when I have smaller, you know, smaller regression equations as well. What I can also do is if I'm thinking about interpreting this SAT score variable, this is the coefficient is the expected increase in GPA from a 1 unit change in the X variable. So today we focused a lot on the student athlete, which was just a 0, 1, it was binary. But if we have a more continuous variable like SAT, a 1 unit increase is 1 more point. Well, if I want to know the effect of, you know, scoring 75 points higher, how would I do that? Well, if I know the effect of 1 point, the effect of 75 would just be take that 1 point and multiply it by 75. So I can get the effect of 75 points, scoring 75 points higher in the SAT score pretty quickly. Okay? So that was some stuff that we kind of did last class, but I just wanted to kind of go over it again with this you know, regression that had a fewer variables in it. Now, one thing that we might start to think though is, okay, here's the effect of 1 point, or 75 points, but I don't know, maybe the first point I score higher on SAT, like going from a 1,000 to a 1,001 is different than going from a 1,500 to a 1,501. So if it, you know, the increase matters depending on where I'm at, really what I'm thinking about here is something that looks like this. So everything that we're doing, I kind of set this up as, right, we're looking at data, and we're drawing this line of best fit, right, but it's a linear line, right? It keeps the, you know, every 1 unit change in our X variable, doesn't matter where we're at, if we go up by 1 unit, the predicted Y variable goes up by the same amount, right? That slope is constant. What's probably going to occur, you know, and just to kind of mention this, so this is what we were doing when we only had 1 X variable. When we include several X variables, what we're really doing is like drawing a line of best fit. Like you can imagine, if we had 2 variables, it's a line of best fit that's like going through like a 3D kind of matrix, right? Then once you start to include more, it's like you can't really visualize it. It's a line of best fit, but it's going through this matrix and it's more than 3 dimensions, and it's really hard to picture, but it's the same idea. What probably occurs more often, though, is occasionally we've got something, maybe our data points look something like this, right? Well, now if I try to draw, maybe I should have exaggerated this a little bit. There we go. Well, if I try to draw like a line that best fits this data, kind of notice like my predictions here are going to be way off. They're always going to be too high. If I could instead draw a line that had some curve to it, well, now my predictions are going to have much smaller errors, right? So if the relationship is not linear, right, in the actual, you know, the original data, I actually need to get somehow, you know, to make predictions, I need to be able to force that relationship between this X and Y variable not to be linear. Well, how will I do that? Well, for a line, you know, the linear line, we've got Y is equal to A plus B times X. If I want it to have some curvature to it, b times x plus c times x squared, right? Well, if I had a variable here, these are really just my coefficient amounts. I can square x and include it as a separate regression, or sorry, separate independent variable in my regression. So we go back to this worksheet. I'm going to insert this here just to kind of highlight. And I'm not going to expect you to do interpretation of these squared terms. I'm showing you this right now to really show you the power of what we could do with linear regression, right? So this part right now is kind of outside the scope of this class, but it does allow us to just think about linear regression better in general. So if we go to data analysis, I've got my y variable as GPA. I'm just going to include SAT, and then this other column was a variable I created, which was just the SAT score squared. So what that does, right, is it allows me to do something like this. Right? So here's my regression output. And really what I'm thinking about what I have now is GPA is, here's the intercept plus B times SAT plus C. Well, I'll keep this the normal convention. So we'll call this B1 times SAT score and B2 times SAT squared. So this gives me the coefficients on both of these. And if you notice, the p-values this is 0. So really that's saying the squared term is significant. That this is not just a linear relationship, there is some curvature to it. Right? So what this would allow me to do is make better predictions, right? Now that I have these coefficients, I plug in these coefficients, and then for any SAT score, I can come up with a more accurate prediction of GPA, right? If I plug in, I don't know, 1100, now my prediction is going to be on this line, and it's going to be a lot closer to the data points. Whereas before, when I was just plugging in 1100 in up here in the linear, my prediction was going to be way off, right? So, this is would be the next probably set of topics we would cover, things like, including a quadratic term to make sure that we don't force every relationship between an x and y variable to be linear. And when I run these quadratic, I don't just have to do it like this. I could have did something like, I could have included for my x variables, SAT and SA squared, and I could have included everything else as well, right? So I could run that regression. Notice my R squared is just creeping up a little bit higher, getting closer to 30. But yeah, so, this linear regression stuff, I always enjoy it. I think it's really powerful. We can make, predictions about the values of different variables. We can understand the relationships that exist. If we start to see things like here, like maybe identify some racial kind of discrimination that's going on, or some type of an issue here that, why are we seeing that black students here are scoring lower on the GPA? Like maybe they're not being given as many resources. Maybe we use the student athlete to start telling positive stories that, being a student athlete teaches time management, but it really just allows us to identify things that might be problems or really investigate certain relationships. And it's really a powerful tool. So I will always, I love talking about this stuff, but if you guys ever have any questions about kind of what to do kind of after this class, there's a couple other courses. If you're thinking about trying to bolster up, I would tell every finance major, with the econometrics course here would be great to take, because when an employer sees that on your resume, that lets them know you have the ability to at least interpret some pretty powerful stuff, at least the ability to learn some of the different statistical programs and doing some work with data. So if you're interested at all in kind of taking more stats after this class, always feel free to reach out. For next week, what I'm going to do is keep going through more linear regression examples. So I've told all my sections, your last one, that either today or over the weekend, if you have an idea or a topic that you just think is interesting and you would want to see, me work through some examples with data related to that, I'll put an announcement on Canvas that gives an idea about what some of the data sets I have are, but really I can get data on just about anything. That way I'm making sure that what I'm talking about is not just interesting to me, but it's also interesting to you guys as well. I think someone already emailed me, my earlier section, I mentioned that I've got like shark bite data. We can kind of play around with that. So, but we'll be doing more linear regression on Monday, just more examples, and then kind of transition Wednesday and Friday of next week, working through some of those practice exams, and then that'll take us into final exam week. So I'll kind of early next week have more to say about the final. I pretty much have it written. Just give some more details next week about that. Okay. If there's no more questions, I will have a good weekend, and I will see you guys on